confront some of the general statements about properties of quantum gravity with actual computations in a well-controlled framework, ideally. As we just heard, it's all about getting equal signs and about numbers and not just about twiggles, and string theory is precisely the framework that has the potential to provide this for us. In this spirit, we can hope to get new information from string theory about various Swampland constraints, thereby checking the Swampland conjectures and maybe even arriving at a sharper formulation on the one hand. On the other hand, we can also think about how string theory is able to meet all those constraints. So how can string theory and how can the underlying string geometry know about the quantum gravity constraints, which are derived or argued for in a completely independent manner? In this talk, I'm going to follow this program in the context of open string theory. So I'd be discussing the realization of gauge theories and their interactions with gravity in theories where the gauge theories come from branes, from open strings, and where these gauge theories are the ones that in principle will be the standard model in a consistent or phenomenologically relevant compactification. So we will start by first looking at the oldest such conjecture, no global symmetries should arise in a quantum gravity theory. And in the context of string theory, we can ask quantitatively what goes wrong if gauge symmetries seemingly become global. And answering this question then also provides the answer to another two questions. First, how can the completeness conjecture be realized in open string theories? The completeness conjecture states that the full charge letters of a theory should be populated by actual physical states. This, at first sight, might seem at odds with open string theories where Champatten factors have a very limited set of charges. And then eventually this will be the main part. We will learn about the weak gravity conjecture in the context of string theory, so we will get the equal signs. What can we say about the precise formulation of the weak gravity conjecture? Can the numerical bound be tested, and which form of the weak gravity conjecture is actually realized in string theory? So the main result of this talk is this. We are going to be working in the framework of 6-dimensional compactifications with branes in the framework of F theory. 6 dimensions because then we have 8 supercharges, and this it will be giving us a bit of control, but what we say, I think, can be generalized and will be generalized also to 4 dimensions and less supersymmetry. And the statement is this: given the most general such F theory compactification, then whenever there exists a geometric limit in which G-Young-Mills can be taken to 0 while keeping gravity fixed, we can prove in that situation the weak gravity conjecture, in fact, the sublattice weak gravity conjecture, including the effect of scalar fields, and we can precisely determine the index of the sublattice of non-BPS states which satisfy the conjecture. This is in the framework of F theory. However, it has implications by duality also for corresponding compactifications of the hadrodic string with 8 supercharges in 6 dimensions, and likewise probably also below. And it is technically related to the BPS state counting in 5-dimensional M theory. So that's the upshot, so to speak. From now on, you can in fact go and catch a plane. So we are working in F theory in 6 dimensions, just a very brief primer. This is a compactification to 6 dimensions on an elliptically fibered Kähler. So this important point is that the compactification space is 2 complex dimensional. It's a Kähler space. And the gauge symmetries are coming from 7 branes which fill 6 dimensions and which wrap curves on the internal space. And all we need to know are 2 things. First, the scale of gravity, the Planck scale, is controlled by the volume of the 2-dimensional compactification space, the 2-dimensional complex Kähler surface. And second, the inverse gauge coupling squared of those theories is controlled by another volume, namely by a volume of one of those curves, by the curves which are wrapped by the 7 branes. This is true for non-abelian branes, then we have just a stack of branes. It's also true if we have abelian gauge groups, then the formulation is a bit more complicated, but we can still think of an effective 7 brane simply wrapping a curve in the base, and the volume of this curve will set the inverse gauge coupling squared for us. So if we think about the interplay of gravity and gauge theory, we have to understand the interplay of these 2 geometric scales. So the slightly more detailed summary is this. we will be asking what happens if we take the Young-Mills coupling to be 0 continuously, geometrically, while taking the Planck scale finite. And of course, by now, we all know exactly what must happen by following field theory intuition as formulated in a number of conjectures. According to the weak gravity conjecture, gravity should be the weakest force, and in the presence of gravity, there should be no global symmetries. So this process must not happen unpunished. In fact, this limit, this offensive limit, should therefore be at infinite distance in moduli space, and the effective theory should break down. There should be something like a quantum gravity censorship forbidding this. And this phenomenon has been discussed from various viewpoints in various different corners of quantum gravity in a number of papers. We've heard about it in a number of wonderful talks this week, beginning in particular with Irene's talk, who was discussing this in the context of four-dimensional type 2b compactifications of n equal 2 supersymmetry, and many more. And again, we are going to discuss this in the context where the gauge symmetries come from branes, so not in the Raman-Raman sector. And the main results are indeed, first of all, indeed, if we start with the gauge theory and take a limit where the gauge coupling goes to 0, then this indeed will be found to lie at infinite distance in the Kähler moduli space, hence it cannot be reached. The reason why it cannot be reached is because we will be finding an infinite tower of charged states, namely we will be finding charged weakly coupled strings which are tensionless in that limit and which will hence be destroying the effective field theory, if you like. And the intuition, and we'll come to this in a second, is the following, but this is very easy to remember. There will be some 7 brane, some curve that gives rise to our gauge group. As this gauge group becomes small, as this gauge coupling becomes small, the corresponding curve here must become infinite, and we will show that necessarily there will be another curve that becomes very small, and these 3 branes wrapping that curve will give rise precisely to those strings. These strings will lead to a breakdown of the effective field theory, but we can say much more. These strings will be identified uniquely with the critical 6D heterotic string, and it will be weakly coupled precisely in the limit that we need to be discussing here, namely this tensionless limit where G Young-Mills goes to 0. Hence, we will be able to quantitatively analyze the tower of particle excitations of the string. These are non-BPS excitations, so nothing is protected by BPS properties here, but we will nonetheless be able to make statements. And these particle excitations will be shown to satisfy the completeness hypothesis as desperately needed in open string theories. And we will prove that these satisfy the sublattice weak gravity conjecture, including the scalar fields. So the analysis at a technical level comes in 2 parts. First, we have to analyze the geometry, so what's really going on here, and then we have to analyze the strings. So the first part will be geometric reasoning, and the second part will then be CFT reasoning, so to speak, or analysis of the so-called elliptic genus of those states. So these are the 2 technical ingredients that we will now come to. Point 1, geometry. I will only be very brief. Proving all these statements takes a few more pages, we're in the paper, but I will at least give an idea or outline briefly what the situation is. So we are interested in a limit where the volume of our compactification space is fixed, so we have gravity kept, and the volume of a curve wrapped by a 7 brane must go to infinity so that G Young-Mills goes to 0. This is the limit, the pathological limit we want to study. And the result is that in such a situation, there must necessarily exist another curve, C0, different from this, which intersects the curve wrapped by the 7 branes, and whose volume goes to 0 as the volume of this curve goes to infinity. The intuition is that if we have a finite volume surface, and we want one curve to become very, very large, then the surface must become very, very thin, so to speak. So the normal direction, if you like, must become very small. And this statement is indeed true in full generality. So not just in case of vibrations or tori, it's true in full generality. So how can one show this? One starts by making the most general ansatz for the Kähler form on that surface. So by expanding in generators of the Kähler cone. And then one implements those requirements one by one and uses properties of Kähler geometry. So the first requirement is that some curve must go to infinite volume by assumption. So there must be one Kähler direction, one Kähler generator which is multiplied by an infinite factor asymptotically, such that the volume of this curve, if this generator has non-zero intersection with the curve, such that this volume then goes to infinity. And then we impose that the volume of the base should remain finite. Hence, there must be no contribution from this infinite directions, but since everything is expanded in terms of generators of the Kähler cones, there cannot be any cancellation, so positivity is at play. It's very positive. So j squared has to be 0, and the remaining terms must wedge into something that is also suppressed such that the volume is just n squared, the remaining part of the Kähler in the Kähler cone, which then will be taken to be finite. And this can be made very precise. Now, step 2, once we've parameterized the geometry in full generality, we have to look for a curve whose volume really goes to 0. And the point is, this class J0, which is a generator of the Kähler cone, happens to also describe the curve of the class of a holomorphic curve. So there exists a holomorphic curve, C0, in the same class. And this curve turns out to be a rational curve, it's a P1, and it has self-intersection. So if you believe me that such a curve exists, then you can immediately see that its volume goes to 0, because J0 squared is 0, so n with C0, this is suppressed by this property here, so its volume goes to 0 as the volume of the original curve goes to infinity. C0 with C has non-zero intersection, that's this property here. It follows from this property originally, so that J0.C gives the infinite volume for C, and C0 squared is 0 because J0 squared is 0. And this can be proven using non-trivial facts about the Mori cone on the Kähler surfaces. So again, the situation is, we have a surface, its volume remains constant. We have a curve whose volume goes to infinity. This means that the gauge coupling squared inverse goes to 0. And we have another curve C0 which intersects this curve. Its self-intersection is 0, and its volume goes to 0 as the original volume goes to infinity. And that's the most general case. This limit is not always possible to take, but whenever we can take a limit G-Young-Mill squared to infinity with volume of B finite, this curve C0 exists. And that's a huge constraint. So we can now go on and analyze this geometric limit according to the field theory intuition or the quantum gravity conjectures that we're after. So the first question was no global symmetries, something must go wrong, or this limit should not be attainable in the first place. And indeed, this is the case here. The limit t goes to infinity turns out to be at infinite distance in the moduli space. We know exactly the metric on the tensor branch moduli space of the 6-dimensional theory, and a short computation shows that indeed the distance is related to this factor, to this parameter t in here in this way. So we're at infinite distance as expected. Second, the Swampland distance conjecture is satisfied manifestly. It says that there should be infinitely many states, and in fact, in this case, charged states, which become massless at an exponential rate. The states in question are strings. The strings are D3 branes wrapping this curve in question, and their tension is therefore given by the volume of the curve C0. This is precisely this curve here, remember, whose volume goes to 0. So the tension goes like 1 over t, which is e to the minus the distance. So they go to 0, the tension goes to 0 exponentially fast, in perfect agreement with the Swampland distance conjecture and also with what has been observed in other contexts. This is only a partialist, apologies for omissions. There have been lots of work on this. But now comes the actual part of this talk. Namely, we now want to be more quantitative about those tensionless strings and see what exactly they imply. This can be done quantitatively because we know how to compute the world sheet theory of this effective string. The effective string, again, comes from a D3 brane wrapping a curve on this base, so this gives an effective string in 6 dimensions. So the first thing to do is, of course, analyze the world sheet fields on that string. This can be done because we start with a single D3 brane. This is an n=4 super Yang-Mills theory. We must reduce it on that curve and analyze the theory in the extended directions, i.e. along the string. This is done in terms of a topologically twisted reduction of the n=4 super Yang-Mills theory that has been worked out in these papers in the past. And the result is that we get a 2-dimensional field theory with 0,4 supersymmetry along the string. So it's a chiral theory along the string. And importantly, since the string curve intersects the 7-brane curve, there are necessarily charged 0 modes from the 3,7 sector here charged under the gauge group, which lead to an effective charge of that string. More precisely, these are precisely 16 left-moving chiral fermions with no bosonic partner, and this, together with the properties of this curve C0, uniquely identifies this string as the 6D heterotic string. And it's in fact the critical heterotic string. It's the critical heterotic string, whose excitations include in particular the graviton. So we don't need heterotic duality at all to make that statement, but it sheds important and interesting light about the role of the heterotic theory itself. Namely, this statement that this is the heterotic string is particularly obvious in the special case when the base on which we compactify F-theory is itself rationally fibered. So when F-theory has an obvious heterotic dual. So suppose the base is one of those Hirzbruch bases, so with a P1 fiber with a fiber. Taking this limit, then it turns out that the curve C0, which has to be wrapped by the string, must be the fiber of that Hirzbruch. Hence, there exists a heterotic dual. The heterotic dual is just the perturbative string on a K3 surface, elliptically fibered over the same base. And as is well known, the heterotic string of that perturbative heterotic compactification is precisely a biduality, the effective string in F-theory wrapping this C0. And more importantly, the coupling, the string coupling on the heterotic side goes to 0 precisely when the volume of the fiber goes to 0. This is exactly the tensionless limit. Hence, we're in excellent shape to make quantitative statements because we are precisely in the ultra-perturbative limit of the heterotic string. However, this logic goes through more generally. Suppose now we are on a general base, not just a Hirzbruch base. Then there still exists a heterotic dual, but it's less obvious. The heterotic dual now contains also extra NS5 branes because we have more tensors. And this can be made very precise with the help of type 2A duality, type 2A heterotic duality, as we discussed in the paper. And the working assumption, and we can justify this also quantitatively in examples, is that away from those defects on the heterotic side, we can still treat that string quasi-perturbatively in this tensionless limit. So the fact that we are now interested in these excitations of a weakly coupled heterotic string is good news because we can in principle compute. However, even if it's weakly coupled, computing the full partition function is completely out of reach because we are not only working on the torus, but we are working on a non-trivial background. What can, however, be computed is the so-called elliptic genus of the 6-dimensional heterotic string that was found many years ago by Bert Strelickens, who's in the audience, and has been discussed in great detail from a heterotic perspective. This elliptic genus counts a subsector of the non-BPS string excitations, and it hence gives us information of the full information, but partial information about the spectrum of the theory. The elliptic genus is defined, if we recall, as a particular weighted trace over the string excitations on the world sheet with suitable insertion of the fermion number operator. This is the usual insertion that we also know from partition functions, and in addition, we want to add information about the charges of those string excitations, so we weigh this trace by a so-called fugacity with respect to the global symmetries of the string. Now, the global symmetries of the string are the gauge symmetries of the ambient space, and from now on, just for simplicity, I'm assuming that the gauge symmetry that we're talking about is an abelian symmetry. Everything goes through also for the non-abelian ones. So this weighing here of the trace tells us something about, gives us information about the charges of the corresponding states. So this elliptic genus is a beautiful object to study by itself. It contains information, first of all, about the trace of the left-moving excitations, because we are always localized on the right-moving ground state. But one can argue that these can always be paired with corresponding excitations from the right movers to produce physical states. Hence, we get a subsector of the non-BPS particle excitations. So far, so good. But now we need to compute it and evaluate it in full generality. And the chain of arguments, in fact, identifies this object, this elliptic genus, with the genus 0 prepotential of the topological string on the same elliptic fibration that also describes F-theory. Just a quick summary what the arguments are. The idea is as has been discussed in great detail in the past in many works, that if you start with F theory in 6 dimensions and reduce it on a circle, you're back in 5-dimensional M theory. So if we take a string and wrap it on a circle, we get a particle in 5D, and that particle, unlike the string excitations, are BPS in 5D. So we can translate the wrapping number and the KK momentum of the wrapped string to the quantum numbers of the particles in 5 dimensions, i.e. we are counting now M2 branes in the geometry of the Calabi-Yau threefold. And by an ingenious trick, one can relate this counting effectively back to the counting of the excitations of the string in 6 dimensions. So the index of the 6-dimensional string non-BPS excitations is counted by the Gupa-Kummer-Waffer or BPS invariance of the 5-dimensional BPS strings. And then looking a bit more in detail, one can identify the correct object indeed with the genus 0 BPS invariance. This object is very constrained by its modular properties, because essentially we are looking at an elliptic genus on a torus, so it must transform well under torus, under modular transformations. In particular, it has a particular index which governs the behavior of those transformations and which must be computed, and we did this. The important thing is that this index governing those transformations is again given by the intersection of the original curve with the 7-brane, with the curve wrapped by the string. So again, this geometric information will then manifest itself in the properties of that string. And this object can be analyzed based on these properties very, very generally in full generality, but can also in examples be computed by making use of mirror symmetry techniques on elliptic threefolds. And now comes the important point. This is what we need to take out of this. Without even looking at at concrete examples, just the structure of this object itself, the mathematical structure itself, the modularity, show us that the maximal charge per excitation level n contains a sublattice of charges of a particular index which satisfy this rule. So for every charge q equals 2m times k, where m is determined geometrically in this way, there exists a state at excitation level n with satisfying this relation. This is completely general, but it can also be checked in concrete examples by using mirror symmetry. For example, here we are looking at an example which does not have a purely perturbative heterotic dual. We compute the Gupa-Kummer-Waffer invariance, find a full expression, and can read off the charges and indeed check this general behavior. And this is what is plotted here. We have here the excitation level of the states of that string. And here I'm drawing the maximal charges per excitation level. So the maximal charges are all the blue dots. And a particular sublattice of charges lies on this curve, q squared equals 4m times n. These are those red ones, and you can see that they are always at a good distance of essentially 4. Yes, or 4, this should be a real line. So what does this tell us for our conjectures? First of all, the completeness conjecture. Again, it states that at every point in the charge lattice, there should be a physical state. And indeed, we see this. Each charge q is populated by some state. And if it were not for those extra closed string excitations, we couldn't satisfy it. In an open string theory as such, this is not satisfied. So ironically, we need, even though we started with an open string theory, we need the closed string from the heterotic string here to save the day as far as the completeness conjecture is concerned. But more importantly, we can now verify that the sublattice weak gravity conjecture is indeed satisfied. To this end, we need another ingredient, namely we need not only the relation between the charges and the excitation level, but also between the physical mass and the excitation level. In general, we would have no chance of knowing that relation, but in the particular limit that we are taking, this is the perturbative limit, and there we can use the perturbative relation between mass squared and excitation level in terms of the tension. We can plug everything in, express n in terms of m squared, plug in particular geometric relations for the different volumes which govern the Jiang-Mills coupling and the tension, and what we find is this relation on the spot. G squared Q squared equals m squared plus 1, which is bigger than m squared over m plugged to the 4, which is set to 1, st to infinity. And this is precisely the relation needed in order for the sublattice weak gravity conjecture to hold. Namely, if you recall, there are two equivalent ways to compute that particular limit. One would be to require that dilatonic Reise-Nordström, so charged black holes, should be able to decay. In the present context, we have to check which are the dilatonic fields, the scalar fields that couple to Young-Mills. We have done this after canonically normalizing. This is the result that we find. It fits precisely into this framework of dilatonic black holes with alpha equals 1. And according to this general analysis in d dimensions, the bound, the weak gravity conjecture bound that must be satisfied now has two contributions, one from the gravity part and one from this dilatonic coupling. And taking alpha equals 1 gives precisely 1, which is what we find. Alternatively or equivalently, we can approach this by the logic put forward by Errand-Palti, by testing for the so-called scalar weak gravity conjecture, namely by saying there must exist some weak gravity conjecture particle for which the Coulomb force should be bigger than the gravitational force plus the Yukawa force. Which Yukawa force? Well, every particle in supergravity couples to some scalar field because their masses are controlled by scalar fields. Again, a detailed computation shows that the mass of the scalar which controls the mass of the scalar field is exactly the same scalar also responsible for this coupling. And working out the Yukawa interactions, we find again exactly the same bound. So to summarize, we have here this upper red line for a sublattice of states, and the blue line, this is the line that should be satisfied by the weak gravity conjecture, and up to the shift of 1, this famous shift of 1 due to the vacuum energy on the string, these two precisely agree. And what I find pretty amazing is that this red line, the one that we find from string theory, was computed purely based on the arithmetics of these Jacobi forms, if you like. The lower line is governed by requiring the Coulomb force must be bigger than gravitational plus Yukawa force. These are two completely different objects, and obviously, or apparently they still agree. I should stress one thing. Our derivation is valid in the limit where G Young-Mills becomes very small. This is the tensionless limit. Why? Because the charge to the mass to excitation level relation is true for the perturbative string. And also because we had to use various geometric properties of this particular limit that we are taking. It would, of course, be interesting to discuss what happens at more general points in moduli space, and what happens if we take into account corrections. So this is, if you like, the tree-level approximation for also for the weak gravity conjecture side. In general, both the masses of the states, of the string states, but also the required bounds will receive corrections. We heard about this in this conference and also just today, and it would be interesting to see how these relate. So let me summarize. We presented a systematic study of quantum gravity constraints for 6-dimensional open string U1s or non-abelian gauge groups as well. We saw that as the gauge symmetry becomes global, a global symmetry asymptotically, while gravity is kept dynamical, there is a tower of infinitely many charged states. They are non-BPS. They are the excitations of a 60 critical heterotic string, and they satisfy the weak gravity conjecture. This behavior, I should say, is very different from the behavior that you find if you shrink a curve with self-intersection negative as opposed to 0, as in our case. This leads to the strongly coupled SCFT limit, which is at finite distance in moduli space. And it's tempting to speculate what the difference is. One potential difference might be that the charges of these, that the masses of the states that one finds here, due to renormalization effect, because it's a strongly coupled theory, will be pushed to infinity in the SCFT limit so that we don't get an infinite tower of master states. But this remains to be seen. And one thing I would like to stress is the mathematics that realizes the weak gravity conjecture. On the one hand, the no global symmetry and the Swampland distance conjecture rely on specific properties of Kähler geometry and Morris-Cohn theorem. The completeness hypothesis and the weak gravity conjecture on detailed aspects of these weak Jacobi forms and their modular properties. And to me, it's absolutely crazy that these weak Jacobi forms know about the weak gravity conjecture. So for me, this is really a miracle. Okay, so all that remains for me to say now is to really thank the local organizers for their absolutely amazing work and this fantastic conference. It is basically impossible after such a great meeting to announce another meeting, but we'll try our best to not fall back too much and cordially invite you to the String Pheno conference next year at CERN. It will be preceded by a week of a string phenomenology, string geometry, Swampland Conjecture Theory Institute, and we all hope to see you next year at CERN for the String Pheno. Thanks very much.
Thanks, Timo. We have time for a short question.
Hi, thanks for the nice talk. So I have this question that you said you need, so this calculation which you do for the tower of states for the Swampland distance conjecture, that you can do for a general Calabi-Yau manifold in this case, right?
Yes.
So, and you can always find these curves C0 and C2 that you had. I mean, does that work all the time, or
no,
other cases
no.
when it
there are
won't work?
Very good questions. Yes, I briefly mentioned it. There are situations where you cannot take that limit. For instance, suppose you do F-theory on a base P2, which just has one Kähler class. Then you cannot make the volume very big then you cannot take a curve to be very big while keeping the total volume finite, because there's only one class. You have only one directions to go. In this situation, you simply cannot take such a pathological limit, and hence the question about Swampland distance conjecture, as far as this is concerned, as far as the relation to gauge symmetry is concerned, would not arise. So what we did is the most general situation where you can take the limit.
And just one more?
I think we should cut this short, because there's the colloquium and the speaker of the colloquium has a plane to take later on. So apologies for that. Maybe we can continue discussing for the coffee. So this closes the session and the workshop. So let me thank all of you for coming, and let's hope that you can visit the IFT soon again. Now we'll have the colloquium pretty soon, so we'll have just a 10-minute coffee break. Okay, thanks a lot.